This puzzle is really interesting, I think, because it looks really complicated, but it looks like you can solve it with just simple high school SOHCAHTOA trig. You can see the video I did on basic trig to understand that, and I'm going to move kind of fast on this and assume everybody knows basic trig. This story could be a plot in a TV show or a movie. The good thing about TV shows and movies is they don't have to be completely realistic. So maybe this scenario is possible, maybe it's not. This is how to use some triangulation to find the location of a shooter with using some 3D geometry or 3D trig. Lately I fell into the rabbit hole of triangulation of a sound or trilateralization of a sound, whatever you want to call it. So I've been exploring all those paths and seeing where they'll take me. So here we have a shot locator. It has 4 microphones. We have an up microphone. Actually, I'll say this first. We have one that goes east and west. We have one that points up, and we have one that goes north. So here's north, up, and east. That makes this microphone right here simultaneously the down, the south, and the west microphone. If sound is traveling in line with 2 of these microphones, it'll take 1 millisecond to travel from one to the other. To get 1 millisecond, you take Mach 1, or the speed of sound, of 343 meters per second. Multiply by 100, you get 34,300 centimeters per 1,000 milliseconds. Divide by 1,000, and you get 34.3 centimeters per millisecond. So let's say these microphones are spaced out 34.3 centimeters apart. There will be a little bit of a variation with temperature and wind, but that won't make much of a difference. You can see the other video I did on that. In that video, I went into extreme detail, calculating the error rates if the speed of sound was increased by 10 or 20%, which is an unrealistic amount of increase. But in the video I showed that if you do the calculations correctly, you will have very minimal error. Also, I'm not worried about echo interference because these microphones will be in direct line with the sound wave, and they'll be far enough away from anything else so the sound wave won't bounce off of something else and hit them and cause interference. So we'll just be looking at the initial sound wave that hits these microphones, and we can ignore any further sound waves from echoes. For this story, let's say there's a squad of soldiers up in the mountains somewhere. The inspiration for these mountains were the Hindu Kush mountains north of Kabul, but they could also be the Caucasus or the Balkans or whatever. And let's say there's a highway right here that passes through the mountains, and there's been a sniper up there taking pot shots at the convoys as the convoys travel through the mountains on that highway. So now we have a squad of soldiers up here on the mountain somewhere hiding out, waiting for the sniper. They have a shot locator device right here because these mountains are very far apart and there's a lot of places to hide. And let's say the sniper is tucked up underneath a couple of large boulders, and not even the barrel of his gun sticks out. So he's got a nice little tunnel he's shooting from, and he's well protected from any airburst if there were any artillery or planes that were going to drop anything on him. So to take him out, you have to have a direct hit. Okay, so the shot locator device right here malfunctioned, and all we have are the raw numbers of when the sound wave hits the microphones. So we have to use these raw numbers to determine the exact location of the sniper. Also, let's say that the part of the device that can determine the distance to the sniper, let's say that part works. The volume or amplitude of sound drops off according to the inverse square law, and that's because sound spreads out as if it's on the surface of a sphere. So I've read that every type of firearm and every type of ammunition has been cataloged with these devices. So when they hear a sound, they'll know the caliber, the rifle, and the distance to the shot. So let's say the sniper's hiding out there somewhere 1,000 meters away or 1 kilometer away, which is a little over half a mile, and he's shooting at some traffic down below on the highway, and maybe he's shooting at you guys while you are up here on this mountain. But you guys are all tucked in behind a bunch of boulders and you're protected. So now you just kind of have to hang out there and wait and see if you can find the location of the sniper. And for our TV show or movie or whatever, we could say that the sniper is inexperienced. So he's just camping right there underneath the boulders. He's pretty happy, pretty comfortable, and he doesn't know that he's supposed to move around. The squad here is up in the mountains, and so that sniper could be up high shooting down or down low shooting up, and that's why we have the 3D array for the shot locator. Like I said, I think this would look really complicated to anybody, but I'm going to try to break this down and make it look super simple for anyone that has had just basic SOHCAHTOA trig. Okay, so first off, this microphone picks up the sound at 0 milliseconds. It's the first one to get hit. This is the east microphone, and then the north microphone picks up the sound next at 0.18 milliseconds. The up or high microphone picks up the sound next at 0.37 milliseconds. The microphone right here that serves as the south, the down, and the west microphone, even though it's just one microphone, it picks up that sound at 0.74 milliseconds. So the shot locator computer has been dropped or hit by a bullet from the sniper, or otherwise doesn't fully work. So it will give you the raw numbers, but it cannot compute the numbers, so you'll have to do that yourself to find the exact location of the sniper, because you're going to have to call in a direct missile or an artillery shell, because this sniper's tucked up underneath some pretty big boulders, so an airburst may not get him. And we could say that since the squad up on the mountain has radio contact with HQ, they can send these numbers, these raw numbers, back to HQ so an engineer can look at them and tell where the sniper is. So you can pretend that you're that engineer. Pause the video if you want to figure out how to solve this, otherwise I'll show what I got on the next page. Here's how I set this problem up. I just drew basically a rectangular box, a fish aquarium or a fish tank. We have the x-axis, the y-axis, the z-axis. Microphones are placed here, 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 and here for a x, y, and z axis arrangement. The hypotenuse right there, so we're dealing with a 3D geometry. That hypotenuse is the direction of the shooter, or the direction from which the bullet came. The bullet will follow the hypotenuse, and the sound wave will follow the hypotenuse as well. We have basically a stick leaning up inside of a fish tank, and if there's a light shining directly down on this stick in this fish tank, that hypotenuse, which is the stick, will cast a shadow on the bottom of the fish tank. We use that shadow to calculate distance. X squared plus z squared equals shadow squared. Then shadow squared plus y squared equals h squared, or hypotenuse squared. So we take this x squared plus z squared, replace shadow squared with that, and we end up with x squared plus y squared equals, x squared plus y squared plus z squared equals hypotenuse squared. Here's the numbers I used in case anybody wants to see it. The x-axis is 4, the z-axis is 3, the y-axis is 2, and so we end up with a square root of 29, which is about 5.4 for the length of our hypotenuse. The math on this initially looks complicated, like I said, but I think I can make it look easy. Let's find the angle of the hypotenuse in relation to each axis. We are dealing with 3D geometry here. So if we're talking about, cosine on the x-axis, this will be the distance of the x-axis, which is 4, the hypotenuse, which is the square of 29, and that will give us the angle in relation to the x-axis. Think of this hypotenuse as being able to spin around like this, because this sound wave is going to hit the east microphone and then the west microphone, a certain amount of time later, that is. But if we spin this hypotenuse around, that means the sound wave could come from any direction as we spin this hypotenuse around. So imagine this hypotenuse going up in the air. It's going to go higher than the y-axis, but it has to stay within the confines of the distance of the x-axis. So this hypotenuse could actually travel farther to the north, because notice this is east. That hypotenuse can twist down as it circles around like this. It can actually travel farther to the north. So it can go up, it can go north, it can go down, and it can come back around and go to the south. It can swing around this way. So let's say we determine the angle here between the x-axis and the hypotenuse to be 40 degrees. So what that means is this hypotenuse could actually point anywhere from east 40 degrees to the north, and east 40 degrees to the south, east 40 degrees up, and east 40 degrees down, and anywhere in between, because we are dealing with this hypotenuse that can kind of spin around the x-axis. I guess what I'm saying here is that the triangle becomes a cone as it spins around. and the location of the shooter will be somewhere on the surface of that cone. So remember that, because when we get this angle, it'll actually be a range that ranges somewhere between north and south. It'll be east so many degrees to the north, or east so many degrees to the south. And same thing with our y-axis and our z-axis. Also remember, when this hypotenuse swings around the y-axis, it has to stay within the confines of the length of the y-axis, but it's actually going to swing out, and the end of the hypotenuse here will actually go out farther than the length of the z-axis. Okay, so that's the setup, that's the logic. In order for me to get these angles, and what I did is turn the angle into a cosine, and then I turn the cosine back into an angle so we can solve it backwards, and you'll see what I mean. So that's it for the whole schematic. Now if you just look at this here, let's not even do any math. Let's just look at the microphones and see from which direction that shot came. Pause the video if you want to figure it out, otherwise I'll show what I got. Notice here, the east microphone gets hit first, therefore we know the shot is coming from the east. Then, which microphone gets hit next? It's the north microphone. So therefore we know the shot is coming from the northeast. And then which microphone gets hit next? The high microphone, or the one that's up. So we know the shooter is shooting from the northeast from a high location. So I said east, north, and up, or northeast and up. So we have it narrowed down right there without doing any math. I always encourage people to pause the video at any point so that they can try to figure this out on their own, and I'll show the next page. So here, x-axis, like I said, I'm going to try to make this look easy. With just the x-axis, we only have two microphones we have to worry about, the east and the west. The sound wave is the dotted line or dashed line. It comes down like this, like my pen, hits this microphone first on the east, comes down and hits this microphone on the west. The direction of the shooter, or the origin of the shot, will be perpendicular to the sound wave. If sound was traveling directly in line with these microphones, it would take 1 millisecond to cover the east microphone and then the west microphone. But it doesn't take 1 millisecond, it takes 0.74 milliseconds. And here's the number where I got that. Hits the east microphone at 0 milliseconds, and then the west one at 0.74 milliseconds. What I'm doing right here, I take time, I turn it into distance. So this could be, for example, 0.74 meters, which it's not. I'm just using that for an example. But then I take the distance, or the length of this leg compared to the hypotenuse, and then I will have the angle from which the shooter is shooting. Here's the important thing to remember with this whole video that I'm doing. What we want is the distance that the sound wave travels after it hits the first microphone. So the sound wave hits this first microphone, the distance it has to travel is 0.74 milliseconds, because I turned time into distance. So for all these calculations on the X, Y, and Z axis, we want the distance that the sound wave travels after it hits the first microphone. And maybe this picture right here, since I'm not showing the other axes or the other microphones, you can kind of imagine this triangle spinning around into a cone. So we just take the arc coast of 0.74 over 1, which is adjacent over hypotenuse, and this is 42.4 degrees. So we know the shooter is somewhere located to the east, and anywhere from east 42, actually I wrote it right here, east 42 degrees north to east 42 degrees south, or east 42 degrees up or down, because we're looking at a cone, and the shooter is somewhere on the surface of that cone. I put a star next to the 42 degrees north because we already know that the shooter is in the northeast quadrant. And that was from the just the logic we deduced from right here with no math. Northeast and up is the direction of the shooter. For the y-axis, there's one extra step. Right here we know that the sound wave hits the east microphone at 0 milliseconds, and then hits the high microphone at 0.37, and then hits the low one at 0.74. So we need to know the time difference between the high and the low microphone, because we're dealing with the y-axis here, and so we have an up and a down, or high and low. We take 0.74 minus 0.37, and we get 0.37 as the distance between the two microphones, or the sound what should I say, the sound distance between the two microphones on the y-axis. And again, this shows if the sound wave is coming directly from low to high or high to low, it would take 1 millisecond to cover this distance between one microphone and the next. But it doesn't take 1 millisecond, it takes 0.37 milliseconds. It's always a good idea to remember to write your units if you're doing a ton of calculations like this, because sometimes after a lot of calculations, and if you're getting tired, well, actually, if you just have a whole page full of calculations, it's easy to forget what the numbers mean. And it's always a good idea to not get overconfident, and so you always want to draw out a proper diagram, and this way you know exactly what it is that you're looking at. So here's the origin. The sound wave travels perpendicular to the origin, hits the high microphone and then the low microphone. And as always, we want the distance the sound wave travels after hitting the first microphone. Now I'm going to do some fancy geometry. Just joking, it's basic geometry. When you're yelling out a direction to your comrades, you don't want to say, look straight up and then 70 degrees down. It's a lot easier to just say, look 20 degrees up from the ground. So that is why I'm going to use this angle alpha instead of beta, and I'll explain that. When we did the trig on the x-axis, I used the cosine of the angle, but on this triangle right here, I'm going to use the sine of the angle. So I'm going to take the sine of alpha. And in this case, if we were to use the angle beta, we would use the cosine right here, because we want this length right here, and this length, or this leg of the triangle, is the cosine of beta. But we don't want the angle of beta, because that would be something like 70 degrees from the vertical, and we don't want to say 70 degrees from the vertical, we want to say 20 degrees from the ground. So here's where we do a little fancy geometry. This is a 90-degree angle. We'll call this alpha, we'll call this beta. And the interior angles of a triangle have to equal 180 degrees. You can see my videos for the proof on that. It was really easy and fun. So what we have here is 90 minus beta equals alpha. And notice we have a 90-degree angle right here. So 90 minus beta has to equal alpha. So this angle from the ground right here going up is the same as this angle right here going down. I'm just explaining this because I'm going to use the sine of alpha and not the cosine of alpha. So we take the arc sine of 0.37 over 1. This gives us 21.7 degrees up. So we know the shooter is 21.7 degrees up in any direction, because this triangle will spin around and make a cone. And next page. Now we do the z-axis right here. The Z microphone on the north side has 0.18 milliseconds. We want the distance between the south microphone and the north microphone. We take 0.74 minus 0.18. That will give us the length of that distance in terms of time. 0.74 minus 0.18, we get 0.56. So here I have the Z-axis microphone. Up is north, down is south. That means to the right is east, to the left is west. Sound wave comes along from some direction. We don't know which direction, but it hits the north microphone first, and then the south microphone 0.56 milliseconds later. And again, we want the distance that the sound wave travels after hitting the first microphone, and that's this distance right here. So what we have here is the height. This is the cos. We take the arc cos of adjacent over height, 0.56 over 1. This equals 56 degrees. So therefore we know the shooter is shooting north 56 degrees to the east or the west. And again, our triangle is actually a cone. It spins around, so this could point 56 degrees to the east or west or up or down. But we already know it's to the east from our initial logic, so that's all we have to worry about. And next page. Let's put it all together now. We have the x and z axis first. Actually, this is all we really have to worry about. East, 42 degrees to the north. So east, 42 degrees to the north. I actually want to turn this into a reference from north. So let's take 90 minus 42, we get 48. So north down to 48 degrees. And this is where the shooter is coming from according to the x-axis. The z-axis is north 56 degrees to the east. So this right here is the z-axis. Take 56 minus 48, we get an 8-degree window. And the reason we have a window is what I explained earlier. We have the x-axis right here. Notice the hypotenuse points up and a little bit to the north. But since we're dealing with a cone and not a triangle, this hypotenuse can actually swing around and go farther north. So notice that's what it did right here. It swung up and went farther north. Now if we look at the z-axis, it's the same thing. The hypotenuse swings around the z-axis. This hypotenuse is located to the east, but if you were to lay this hypotenuse down, it would go even farther east. And that's why we have the z-axis being south of the x-axis. In other words, the x-axis gives a potential location of the shooter, the z-axis gives a potential location of the shooter, and this window is created from the overlap between the x and the z-axis. But this is actually a very narrow range. I'll show how to get the distance of that arc right there, because what we have is a circle. We have an arc length that's on the circumference of that circle. 8 degrees over 360 degrees will give us that angle right there, or the percentage of that angle. This will equal the arc length over the circumference. And this makes sense right here. If you have a 90-degree angle, 90 is 1/4 of 360. Therefore, this arc right here will be 1/4 of the circumference. That's all I'm doing right here. And we already know the shooter is 1,000 meters away, so circumference is 2 pi r. So we solve for arc. We get 44 meters. The length of this window at 1 kilometer away is only 44 meters. So cut that number in half and you have 22 meters. So if you were to go out there and stand in the middle of that arc, you would be in the center of a circle with only a 22-meter radius, which means you could stand there and have a conversation with them. By the way, I mentioned on one of my other videos, I'm not an expert on electronics, shot location devices or anything, and I really know nothing about the military, but I do read a lot. So I've read that, I've read many times that the preferred anti-sniper method is artillery or ordnance dropped from aircraft. And that's because the sniper is going to be tucked in to a tiny little area where you can't see him. And typically he's going to have a decent view of everything that's going on around him. So he'll have concealment and field of view. So if anybody even gets close to him, then they'll likely get shot. And if you had no idea where he was, say it was like some sort of a Stalingrad movie or something where you have these two snipers out there hunting for each other, that takes a very long time and is very dangerous. It takes a long time because you're covering a huge area and both snipers are going to stay very well hidden. So they most likely will never see each other, or they'll never meet. So at any rate, like I said, artillery or ordnance from aircraft is the top choice to combat a sniper. And this particular sniper, like I said, let's say he's tucked in underneath some really big boulders. So you're going to need a direct hit, and maybe an airburst wouldn't work. So this is a pretty, like I said, a 22-meter radius. That's a pretty narrow window. On the next page, I'll show the actual calculations to show exactly where he is. Directions in terms of degrees are usually used in terms of north. So the z-axis runs north and south. So we look at the z-axis and find out what the angle is where the shooter is compared to the z-axis. First, we need the distance of the shadow right here of the hypotenuse. So we will have x squared plus z squared equals shadow squared. And we go ahead and solve for the shadow right here, and that will be 5. Now the z-axis is 3 units long, so we take arc cos of 3/5 equals 53 degrees. And notice I said our window previously was between 48 degrees to 56 degrees, so this is almost exactly right in the middle. And I'll show this picture one more time so you can kind of see what we're doing here. It's the shadow that we're interested in. I'm not considering altitude. I'm just looking at the cardinal direction in relation to north. But since we are dealing with a mountainous region, we will have our direction of 53 degrees from the north to the east. But we will have to go up 20 degrees from our location to the exact location of the sniper. Now, previously, what I did, if you take 48 plus 56 degrees divided by 2, that will give us an average distance here, or sorry, an average degree of 52 degrees. So for our estimate, we say the shooter is at 52 degrees, but he's actually at 53 degrees. What does that mean? We were only off by 1 degree, so 1 degree over 360 equals arc over circ. And so since we're only talking about 1 degree at 1,000 meters, that means the arc length is only 17 meters. So that means in this particular situation, if we went to the midpoint of our window, and that midpoint is 52 degrees, we would only be standing 17 meters away from the sniper. And you could say the shooter, for example, was 2 kilometers away, which is over a mile. Then you would just double this, and 17 becomes 34. So still pretty close. Hopefully I made that look easy. My primary goal and what I like to do on this channel, I like to take things that look extremely difficult and make them look either extremely easy or very easy. But everything I did here is just high school trig. And actually just introductory trig because it's just the basic SOHCAHTOA. I'm not getting into like the length of sine waves or anything like that. By the way, don't be shy about letting me know if there's any errors, either in calculation or logic. As I've said before, I just make this stuff up.